Three-Phase Technical Services presents Infrared Scanning Basics, Thermography Training. Introduction to Infrared Imaging. Welcome to the Thermography course. Here we will learn about thermal imaging basics, the thermal camera, how to measure temperature, thermal imaging interpretation. This course is divided into 5 chapters. Thermal imaging basics. What is it and how does it work? The thermal camera. Important specifications and its settings. Measuring temperature. The object emissivity. Application examples. The environment reflected apparent temperature. How to proceed for thermography in practical. Chapter 1. Thermal Imaging Basics. The objectives of this chapter are: at what temperature the objects emit heat, the energy form that visible light and infrared radiation belong to, explain how a thermal camera makes heat visible to our eyes, an analogy illustrating how IR radiation is converted into a visible image, different phenomena that might occur when infrared radiation hits an object, give examples of situations when visible light and infrared radiation behave the same and when they do not. Electromagnetic radiation. Every object with a temperature above absolute zero emits energy, heat, in the form of electromagnetic radiation. Electromagnetic radiation travels through vacuum at the speed of light. It is characterized by its wavelength. Visible light and infrared radiation. Infrared radiation and visible light are both types of electromagnetic radiation. Visible wavelengths are 0.4 to 0.7 micrometer. Infrared wavelengths are 0.75 to 100 micrometer. Long wave infrared are 7.5 to 14 micrometer. Our eyes is sensitive to visible light. A thermal camera is sensitive to infrared radiation. Sensing heat. Sitting in the sun or around a fire, we feel the heat on our skin. Similarly, sensor of the thermal camera is also sensitive to heat. An electrical signal is generated and translated into a thermal image. Analogy with radio waves. Radio waves has a radio frequency or RF radiation which travels through air. But we cannot see or hear them. A radio converts them into sound waves. The human ears are sensitive to these pressure waves. So we can hear speech or music through radio. Analogy with infrared radiation. Like radio waves, infrared radiation also propagates through air. A thermal camera is a device that converts them into an image visible light that our eyes can see. Thermal imaging basics. With a thermal camera, we can see heat. Heat is also coming from objects we consider to be cold, such as ice cubes, Humans need external illumination to see objects. Only very hot objects emit visible radiation. Let's see image of radiation. In the visible world, we need external illumination. The image we see with our eyes consists of light that is reflected by the object. In the infrared world, the thermal camera does not need external illumination. The camera image shows radiation that is emitted by the object. The thermal image is an image of the temperature of the object. Infrared radiation. Infrared radiation is emitted by all objects. The hotter the object, the more radiation, that is, the more energy. When infrared radiation hits an object, it can be either absorbed, transmitted, or reflected. What happens in a specific case depends on the nature of the object. Beware that IR radiation and visible light may behave differently. Infrared transmission. Infrared radiation passes easily through gases and volatile matter, for example, air, fog, or smoke. It also passes through some thin solids like plastic film. Infrared absorption. Infrared radiation passes easily through gases, but it is stopped by liquids and solids, for example, glass, water, wood, brick, plastics, etc. Reflection, its effects on thermography. The mechanism of reflection is the same as for visible light. Reflection follows the rule angle in is equal to angle out. When using a thermal camera, be aware of your position so as not to make mistake your own reflection for a hotspot. Surfaces may not reflect visible light and infrared radiation to the same extent. The degree of reflection depends on the characteristics on the reflecting surface. For example, a window will reflect a clear infrared image of a warm or cold object. The mirror reflects operator clearly in both visible light and the infrared region. But the tiles below the mirror, however, only reflect the infrared radiation and not the visible light. There are few more effects of reflection on thermography, such as a reflection can be clearly seen in the window in the infrared region, but this is almost absent in the visible light. The visible light passes through glass, but it is not passing through the wall calendar. There is no reflection of the person holding the camera. However, you can see a diffused reflection of the person in the infrared region. Visible light is reflected in the mirror. You can see what is on the TV screen. Looking with a thermal camera, you see only the reflection of the candle. Now let's have a short quiz. What does the thermal image show? A. Heat per square meter. B. Temperature distribution. C. Radiation. D. Transmission. Yes, you are correct. The answer is C. Radiation. Here's another question. Which object emits heat? A. Only objects that do not reflect. B. Only solids. C. Only objects with a temperature 0 degrees Celsius. D. All objects with a temperature above absolute zero. Yes, you are correct. The option correct is D. All objects with a temperature above absolute zero emits heat. Chapter 2. The Thermal Camera. Nowadays, a handheld camera is easy to use. However, a thermal camera specifications are quite comprehensive. Here, we will look closer at some of the most important specifications of a thermal camera. The objectives of this chapter are: describe what the camera's temperature range is related to, explain saturation, explain why the amount of pixel matters when looking at small objects, illustrate the importance of high resolution by giving an example application, define the term emissivity, list some materials with high, medium and low emissivity, illustrate how an object both emits and reflects radiation when placed in an environment. Explain the origin of emitted and reflected radiation. Thermal camera specifications and its settings. Temperature range defines the range of object temperatures that can be measured correctly. Number of pixels, infrared resolution, a measure of the resolution of geometrical details in a thermal image. Emissivity, compensation for the variation, is the emission of infrared radiation by different surfaces. Reflection, compensation of radiation from the surroundings that is reflected by the object. Temperature range. Thermal cameras are calibrated for different temperature ranges. For example, -25 to 250 degrees Celsius, -25 to 100 degrees centigrade, 0 degree to 650 degrees centigrade, 0 degree to 100 degrees centigrade. Correct temperature measurement is not possible outside the specified ranges. Saturation occurs when measuring temperatures above the calibrated temperature range. What is saturation? The image shows a toaster in the infrared region. The temperature range in the image starts at +150 degrees centigrade. However, the maximum temperature is well above this value. Therefore, the area maximum temperature indication has a small red cross right to the digital readout, and the average temperature has a warning symbol. These symbols indicate that the measured values are not correct. Effects of saturation. The temperature range in the image ends at +650 degrees Celsius. All measurement values are within this range and therefore correct. Assuming that all other parameters are set correctly, the temperature scale to the right can be set to any value independent of the selected temperature range. Number of pixels, infrared resolution. At a given distance and within the same lens, a higher number of pixels will allow you to resolve smaller details. Example, measurement spot size at two distances. The adjoining table shows the measurement distance and the thermal camera resolution with the resultant picture quality. Spatial resolution. High resolution, better ability to see small targets at longer distances, better measurement accuracy of small targets. You will be able to find more problems, find smaller problems, improve diagnosis with better image details, find problems you would otherwise miss completely. What is emissivity? Emissivity describes a surface's ability to give off infrared radiation. Surfaces with high emissivity are good emitters and will not reflect much radiation from the environment. Surfaces with low emissivity are bad emitters, and in the thermal image, you will mainly see reflections from the environment. A painted surface is a good emitter. Shiny metal is a bad emitter. Therefore, the valve appears to have a lower temperature than the pipes or the radiator. Emissivities of different materials. In the given picture, on x-axis we have surface quality and on y-axis we have emissivity. Polished and glossy metals such as shiny copper and polished metals have low emissivity, whereas glass, being polished and glossy material, has high emissivity. Plastics, paint, ceramic, etc. has medium emissivity. Worn, aged, rough materials has high emissivity. For example, leather, fabric, sand, etc. Reflected apparent temperature. Now let's have a short quiz. What is emissivity? A. A measure of a surface's ability to give off IR radiation. B. A measure of the color of a surface. C. A measure of the temperature of a surface. D. A material constant. Yes, you are right. The correct answer is A. A measure of surface's ability to give off IR radiation is emissivity. Let's have another question. What is high infrared resolution good for? A. Avoiding saturation. B. Getting rid of reflections. C. Being able to spot small targets at long distances. D. Improving camera calibration. Yes, you are right. The correct answer is C. Being able to spot small targets at longer distances. Chapter 3. Measuring temperature. The objectives of this chapter are: describe the measurement situation, name the settings in the camera used to compensate for influences from the object surface and the radiation from the surroundings. With the help of corresponding visible image, point out surfaces with expected low emissivity in a thermal image. Reflections in a thermal image. Localize areas with a different reflected apparent temperature in a thermal image. Measurement situation. Looking at an object, the camera receives radiation originating directly from the object, indirectly from the surrounding sources, that is reflections. Only the IR radiation emitted from the object itself is related to the object surface temperature. The reflected radiation is termed as reflected apparent temperature. Measuring temperature. To measure the object's true temperature, you need to enter the following data into the camera. First, the emissivity of the object's surface. Second, the reflected apparent temperature, that is, the amount of radiation from the surroundings that is reflected from the object into the thermal camera. Importance of emissivity and reflected apparent temperature. The images show a vent cover. They were taken on a warm sunny day. In the visible image, you see the reflection of the sun. In the thermal image, you can see the reflection of the sun, the reflection of the sky, the reflection of the warm roof. What is apparent temperature? Move the measurement spot from one reflection to the next. Measure 3 different temperatures. All 3 measurements will be wrong if you do not use the correct emissivity and reflected apparent temperature. Plus 3.1 degrees centigrade, minus 3.13 degrees centigrade, plus 44.9 degrees centigrade. Temperature measurement. It is easier to move true temperature of good emitters. This water kettle in the picture is filled with very hot water. The bare metal has a low emissivity, so the uncorrected temperature reading is very different from the true value. The label has a high emissivity, so the uncorrected temperature reading is close to the true value. Now let's have a short quiz. What is reflected apparent temperature? A. The sum of the temperature of all objects in the surroundings. B. The radiation from the surroundings that is reflected from the target into the camera. C. Spot reflections. D. All reflections that are warmer than the object's temperature. Sorry, the correct answer is B. The radiation from the surroundings that is reflected from the target into the thermal camera is the reflected apparent temperature. Now let's have a second question. What parameters do you have to set correctly if you want to measure the true temperatures of an object? A. The spot meter. B. Emissivity. C. Reflected apparent temperature. D. Both B and C. Yes, you are right. The correct answer is D. Both B and C. Emissivity as well as reflected apparent temperature. Chapter 4. Image Analysis. Examples of image analysis for different applications. The objectives of this chapter are: analyze thermal images including the following: localize hot and cold spots, identify reflections, draw conclusions from the thermal pattern and work out what type of thermal transfer is shown in the thermal image. Combine the 3 procedures above with application knowledge and come to a conclusion about the fault or anomaly found. Application example 1. Electrical. This thermal image shows a poorly tightened electrical connection. This causes a higher electrical resistance which leads to an increase in heat. The thermal pattern clearly shows the conduction in the cable. Application example 2. Electrical. This is an image of a high voltage isolator switch that shows a failure on one side of the mechanical connection. Less mechanical force leads to higher electrical resistance. This is also amplified by the copper oxidation. we see a thermal pattern of heat conduction. Application example 3, preventative maintenance. You can see heat leaking from a joint in this pipe. Close to the leakage, the surface of the pipe is warmed up by convection and conduction. This is a very difficult measurement situation due to the low emissivity. You'll have to be aware at the reflections from the other pipes and the light bulbs in the ceiling. Application example 4, industrial. This is an air conditioning HVAC piping system. It is the first segment close to the compressor. The cold area is the result of thermal insulation failure, allowing water to condense and possible even after the insulation. The thermal pattern is created due to differences in heat conduction through the insulation wall of the pipe. Application example 5, industrial. The liquid in the vessel is warmer than the air above it. We see the filling level from outside because of heat conduction through the tank envelope. More heat is conducted when the temperature difference between the inside and the outside is greater. Application example 6, building. These images show double glazed windows in a commercial building. The images were taken on a warm summer day while the sun was shining. You can see clearly on one window is colder than the others in the thermal image. There are two possible explanations. First, there could be a leakage between the panes. In such a case, this window is not insulating well and more heat is conducted to the colder inside environment. Second, the window can be mounted inside out with the low emissivity paint facing the wrong direction. In such a case, it reflects more than the other windows. So it is not warming up but reflecting the cold sky. Application example 7, building. These images were taken during a blower door test and shows the entrance door from inside. The house is under pressurized and cold air is coming in. The thermal image clearly shows two physical effects. First, a convection pattern. The cold air leaks in around the entrance door window and cools the inside of the window in a very characteristic thermal pattern. Second, the reflection of the operator in the window. Application example 8, solar. These images show a solar panel. As the damaged cell gets warmed, we see a pattern due to heat conduction from the broken cells to the surface of the module in the thermal image. Be aware of the reflection from the sun, clouds and the trees when undertaking solar panel inspections. Now let's have a short quiz. When can you see the filling level of tanks with a thermal camera? A. On a rainy day. B. When there is a temperature difference between the liquid and the air above it. C. When the tank is more than half filled. D. When the tank is painted black. Yes, you are correct. The option is B. When there is a temperature difference between the liquid and the air above it. Now here's the second question. What is a typical reason for a thermal pattern? A. Conduction, B. Reflection, C. Convection, D. All of the above. Sorry, the correct answer is D. All of the above. Chapter 5. How to proceed in thermography practicals. The objectives of this chapter are: evaluate the measurement situation, select appropriate camera settings, take a good thermal image, measure temperature correctly with a thermal camera. Step 1. Set a temperature range so that it includes those temperatures you expect to measure. For example, you can choose -20 to 120, 0 to 650 or 250 to 1200 depending upon your application. Step 2. Position and field of view. Check for reflections. Move if needed. Check spot meter size or detailed resolution. Move closer if needed and possible. Step 3. Focus. An unfocused image is not only unprofessional but will also lead to wrong measurement results. Step 4. Enter the measurement parameters: emissivity, reflected apparent temperature. Step 5. Save the thermal image and the visible images. Image optimization. In order to produce a professional image, you also need to optimize the image presentation. This includes selection of a suitable color palette, manual adjustment of the temperature scale, selection of suitable measurement tools, for example, isotherm, alarm above and area maximum. Now let's have a short quiz. What is the characteristic of a good thermal image? A. It uses an appropriate temperature range. B. It is focused. C. It is taken from a good position with respect to reflections and spot size. D. All of the above. Yes, you are correct. The correct answer is D. All of the above. Second question. How can you improve the image presentation when using software? A. By selecting a suitable palette and adapting the temperature scale. B. By changing the emissivity settings. C. By changing the apparent reflected temperature settings. D. By changing the focus. Sorry, the correct answer is A. By selecting a suitable palette and adapting the temperature scale. Now here's a final quiz for you. I hope by this time you have some basic understanding of thermal imaging. So let us start the final quiz. Question 1. High infrared resolution, more pixels enables you A. To measure smaller targets, B. To avoid issues with emissivity, C. To measure cold objects, D. To ignore the reflected apparent temperature. Correct answer is A. To measure smaller targets. Question 2. What will happen if you set an incorrect emissivity value? A. You will see only reflections. B. You will still measure the true temperature if the object is hot enough. C. The temperature reading will be incorrect. D. Nothing, as long as the reflected temperature is set. Correct answer. C. The temperature reading will be incorrect. Question 3. Through which of the following materials does infrared radiation pass through? A. Glass. B. Water. C. Air. D. Brick. The correct answer is C. Air. Question number 4. Infrared radiation and visible light are forms of A. Mechanical energy. B. Electromagnetic radiation. C. Cold. D. Nuclear power. Correct answer is B. Electromagnetic radiation. Question number 5. Which rule does the mechanism of refraction follow? A. Infrared radiation is reflected as visible light. Reflection occurs only at 90 degrees. C. Angle in is equals to angle out. D. Reflection occurs only at visible wavelengths. Correct answer is C. Angle in is equals to angle out. Question number 6. When does saturation occur in the thermal image? A. When measuring temperature above plus 100 degrees centigrade. B. When measuring temperatures above the temperature range that is selected in the thermal camera. C. When using the manual setting for the temperature scale. D. When looking at objects with high thermal contrast. Correct answer is B. When measuring temperatures above the temperature range that is selected in the thermal camera. Question number 7. Which of the following is a good emitter? A. Shiny metal. B. Polished copper. C. Concrete. D. Stainless steel. The correct answer is C. Concrete. Question number 8. When looking at an object, the thermal camera receives radiation that is emitted directly from the object and also reflected radiation from surrounding sources. Which part is related to the object's temperature? A. The sum of both parts, emitted and reflected radiation. B. The reflected part. C. The average of both parts. D. The radiation that is directly emitted. The correct answer is D. The radiation that is directly emitted. Question number 9. It is easy to measure the temperature of an object with high emissivity because A. The reflected part of the total radiation reaching the camera is negligible. B. The object mainly reflects the surroundings. C. Reflections will be absorbed. D. There will be no reflections. The correct answer is A. The reflected part of the total radiation reaching the camera is negligible. Question number 10. What will happen when the thermal image is not focused? A. There will be no reflections. B. The temperature reading will be wrong. C. The emissivity will change. D. The temperature scale will be locked. The correct answer is B. The temperature reading will be wrong. Hope we had a good informative session on basics of thermography. Three-Phase Technical Services, an ISO 9001-2015 certified company, provides thermal imaging for electrical installations with qualified and certified thermographers, using a high-end software tool for report generations. TPTS also offers corrective and predictive maintenance services and annual maintenance contracts.